Intermolecular forces are the forces that condense matter. If you add energy to a system, you will overcome those intermolecular forces and undergo a phase change. So a solid, which is the most condensed form of matter, with the application of energy, will undergo fusion, or melting, and become a liquid. Now, if you remove energy from a liquid, it will undergo freezing, or solidification. If energy is continued to be applied to a liquid, you'll overcome all of the intermolecular forces holding it together, overcome all the attractions between the molecules, and it will vaporize or undergo vaporization and become a gas. If a gas is cooled, releases energy in an exothermic process, it will condense and become a liquid. Now, some solids are able to bypass the liquid phase and actually go straight to being a gas. This is called sublimation. An example of this would be dry ice or carbon dioxide, which is really just compressed into a solid form. Iodine crystals also sublime off. Those are the two most common. If a gas that is capable of going straight to a solid goes back, or the opposite of sublimation, with the release of energy, is called deposition. The amount of energy necessary to vaporize or condense or solidify or melt 1 mole of a solid liquid or gas at 1 atmosphere is known as the enthalpy of, and then whatever the phase change is. So for example, the enthalpy of vaporization is the amount of energy necessary to vaporize 1 mole of a liquid at 1 atmosphere. If you reverse the magnitude of that, so the negative heat of vaporization, negative enthalpy of vaporization, is the enthalpy of condensation. So while it will take energy to vaporize something, it will release energy to condense it. Same goes with fusion and solidification. The amount of energy it takes to melt 1 mole of a solid at 1 atmosphere is the enthalpy of fusion. The amount of energy released when 1 mole of a liquid solidifies to a solid at 1 atmosphere is the enthalpy of solidification. And at any given moment, a solid or a liquid can exert a vapor pressure, meaning that the liquid's molecules or solid molecules on the surface are absorbing energy from their surroundings and becoming a gas molecule. We're going to focus mainly on liquid vapor pressure. Just know that solids are capable of exerting a vapor pressure. So as the molecules on the surface absorb energy from the surroundings, they turn into a vapor. And those molecules collide with the walls of their container, can collide with each other, and can lose energy and return to being a liquid. These molecules that have escaped the surface of a liquid and have become a gas phase exert a pressure on the surface of the liquid. This pressure is what we call a vapor pressure. When the rate of evaporation equals the rate of condensation, the system is said to be at an equilibrium for its vapor pressure. Substances with very low intermolecular forces, meaning they have very low attraction between their molecules, have very high vapor pressures, because more of the molecules can escape to becoming a liquid and exert a greater pressure. These substances are called volatile. So substances that readily evaporate in open containers are volatile. The more energy put into a system, i.e. the warmer it gets, the higher the vapor pressure, because more and more particles have absorbed enough energy to become a liquid. A gas. The more particles that have sufficient energy to overcome their intermolecular forces, the more gas you are producing. So at higher temperatures, there will be more vapor pressure. These two graphs are often overlaid over one another, and you ask to determine which has the greater temperature, temperature 1 or temperature 2. And it's all about understanding the area under the curve. The energy needed to overcome intermolecular forces is highlighted on each, but which one has the greater area under the curve would be temperature 2. So we would say that temperature 2 is greater than temperature 1 because more molecules have enough energy to overcome their intermolecular forces. In general, as molar mass increases, vapor pressure decreases. Why? Because as molar mass increases, not only do you get more protons and neutrons, you also get more electrons. And more electrons causes an increase in polarizability of the molecule, and therefore you have stronger or more instances of induced dipole, or dispersion forces. However, anytime you have hydrogen bonds, this will negate this fact. So for example, water, while having a very low molar mass, actually has an extremely high vapor pressure due to its hydrogen bonds. If we plot the natural log of the vapor pressure versus the inverse of the temperature, we get a straight line. Where vapor pressure is Vp, delta H vaporization is obviously the heat of vaporization. R is the universal gas constant, but since it's all about energy in this unit, we'll be talking about 8.31 joules per mole Kelvin. And lastly, next is T. T is in Kelvin, just to cancel out the R value. And C is a constant characteristics of the liquid. So the slope of each line is the heat of vaporization divided by the gas constant, so the line with the steepest slope would have the greatest heat of vaporization. We use the heat of vaporization to calculate the energy necessary to undergo a phase change. And we often see these on heating and cooling curves. Picture below is a heating curve. We can tell it's heating because as heat is added, temperature is increasing. A cooling curve would do just the opposite. So anywhere where we have a slope, be it positive in the case of a heating curve or negative in the case of a cooling curve, we can calculate the change in the energy or the heat added, Q, by using the formula Q equals mc delta T, where Q is the energy in joules, kilojoules, calories, or kilocalories. M is the mass in grams. C is the specific heat, which is specific to each substance in that particular phase. So for example, for a solid, if we're talking about water, we would use C of solid water, of ice, or in the case of liquid, C of liquid water, or in the case of heating a gas, C of liquid of steam. And delta T is the change in temperature, final temperature minus the initial temperature. Where the energy added, in the case of this heating curve, is kinetic energy because there's a change in temperature. However, during a phase change, there is no change in temperature. So we couldn't use the formula Q equals mc delta T because delta T would be 0. And we would end up with a Q term of 0, which is not possible. We know we are adding energy. So we use a different formula, and it's Q equals m delta H, where the delta H is either the heat of fusion or the heat of vaporization, depending upon what phase change is occurring. And whereas adding or increasing temperature or decreasing temperature dealt with kinetic energy, when we have these plateaus, we are dealing with potential energy. Because the energy added or subtracted is causing the phase change and is altering the potential energy. You'll also notice that during a phase change there is no change in temperature. And this is because the temperature of a substance will not rise again until the phase change is 100% complete, until every single molecule has undergone the phase change. The point at which the vapor pressure of a solid equals the vapor pressure of a liquid is its melting point, which we'll see here in this substance, which must be water, but well, yeah, it says right here, temperature of water, which for water is 0 degrees Celsius. So this is the point at which the vapor pressure of ice equals the vapor pressure of a liquid. of liquid water. The point at which the vapor pressure of a liquid equals the vapor pressure of a gas, or the vapor pressure of a liquid equals atmospheric pressure, is the boiling point. So in this case, this must be at 1 degree Celsius because at 1 atmosphere, because at 1 atmosphere, 100 degrees Celsius is the temperature that water boils. Now, normal melting point and normal boiling point are at 1 atmosphere exactly. So the temperature at which a substance melts normally at 1 atmosphere would be its normal melting point. The temperature at which a substance boils at 1 atmosphere would be its normal boiling point. Changes in phase do not always occur at exactly the melting point or the boiling point. And mainly this deals with the changing technique. This is where we get the terms supercooled and superheated. If a substance is supercooled, then it's at a temperature below its freezing point, yet remains a liquid. This usually happens when the substance has been cooled at a very slow and steady rate so that crystals haven't formed yet, because they lack the degree of organization needed to form them. They can be forced to form by planting what is called a seed crystal. So in the case that this happens, you could scrape the side of the glass with the thermometer that you have in it, and that would break off just the smallest piece of the glass crystal that would give the supercooled liquid enough organizational template or to allow it to form around that seed crystal. In effect, it would look as though a crystal just grew spontaneously, whereas you gave it a small piece to build off of. So this picture shows a supercooled liquid because we see that it's decreasing in temperature. Once it is given a seed crystal, the temperature rises again back to the normal solidification point. In the case of a superheated glass, the temperature is raised above the boiling point, yet remains a liquid. You'll often see this happen in microwave ovens. In fact, I've included a link on the wiki page, or the Weebly page, that will allow you to see this in a Mythbusters episode. Once the liquid's surface tension is broken, it causes it to rapidly undergo the phase change and will often explode. In lab, we often prevent this by putting boiling chips into a flask. These are very porous rocks that have air trapped in them, and this air space or air pocket allows air bubbles to form and therefore keep the liquid from superheating. The final part of this unit is phase change, or phase diagram. Phase diagrams represent the phases of matter as a function of temperature and pressure, because together they can cause a change in phase. Substances at low temperatures and high pressures are typically solids. By typically, I mean almost always are solids. Substances at high temperatures and low pressures are vapors, and in between the two you find a liquid. The critical temperature is the temperature at which a vapor cannot be liquefied. And the critical pressure is the pressure at which a liquid the critical pressure is the pressure required to liquefy something at its critical temperature. The critical point is simply where these 2 points exist. So the critical temperature and critical pressure coordinates. This graph does a better picture, is a better way of showing that. So this is a phase diagram for water. The critical point, the critical temperature for water is 374 degrees Celsius. At that point, you no longer can have liquid water. The critical pressure for water is 218 atmospheres. At that point, you can either solidify or produce a gas. At that point, you can produce water at those high temperatures. You can produce water at those high temperatures. Now, along each line, you find a phase equilibrium. So along this line, I have both solids and vapor existing in equilibrium. Along this line here, I have a solid and a liquid both existing in equilibrium. Along this line here, I have a liquid and a vapor existing in equilibrium. The point at which all three intersect is called the triple point. where all three, solid, liquid, and gas, exist in a phase equilibrium. Here I have another phase change diagram, or phase diagram of water, and I can tell it's water because water is one of the only substances that actually has a negative slope for the phase equilibrium line between solids and liquids, where the solid is actually less dense than the liquid, and that's why it floats. 99.9% of the time you will see this with a positive slope. So for experiment 1, we start with solid ice at 1 atmosphere, so this is a normal conditions, and we heat it up until we get to 0 degrees Celsius, and then at that point we have a phase equilibrium, and if we continue to heat it up we'll have a liquid till we get to 100 degrees Celsius, and then we'll be at a phase equilibrium again between a liquid and a gas until only gas is produced. In experiment 2, we're at extremely low pressures, and at low pressures, as we heat it up, we'll eventually reach a point at which ice will sublime and go straight from being ice into steam. In experiment 3, we're at a low pressure again, but as we heat it up at this pressure, we cross the triple point, so we will have a solid until we reach this triple point, which is just a little bit above 0 degrees Celsius. At this point, we'll go through a phase change, or we'll have a phase equilibrium where solids, liquids, and gases are all present until only gas is produced. Lastly, in the 4th experiment, we're at a high pressure, and as we heat up our sample of water, we start with liquid. We are above the critical point of liquid, so we do not have actual liquid. We have a fluid that is neither liquid nor really a vapor because we have exceeded the critical point.